Bismillah ar-Rahman ar-Rahim. Assalamu alaikum wa rahmatullahi wa barakatuh. In this video, we will discuss the notion of a triple integrals in rectangular coordinates. And for that, we'll work with functions of three variables. We have w equals of x, y, z. For the definition of triple integrals in rectangular coordinates for functions of three variables, we cannot start the definition geometrically, because we cannot really graph this function. For functions of two variables, if you recall, we have z equals of x, y. Here we started the problem with double integrals geometrically by considering the volume problem. When the function f is positive and it is defined over a region R, and this is the graph of z, then we can think of the double integral as a volume of the solid here. Okay, so volume, when f is positive, of course, so here volume, it will be given as double integral of f of xy dA over R. So for functions of two variables, we can start double integral, or we can motivate double integration in an applied way using the volume problem. And in the process, this was given as limit of a double Riemann sum. xij star, yij star, delta A. So this is what we did briefly for functions of two variables. The procedure here cannot be done for functions of three variables, because we cannot really graph a function of three variables. For the graph, we need four-dimensional space. So in that case, how to define triple integrals of functions of three variables? Really, here we used Riemann sum. We use the definition. We generalize the limit of a Riemann sum. Okay. So we use the mathematical definition of a limit of a Riemann sum, ignoring the geometric meaning. Okay. So this is what we do. Okay. So we give a mathematical definition, which is just a generalization of the limit of a Riemann sum for double integrals. So the definition of the triple integral is given as follows. So definition, let f of x, y, z be a continuous function on a closed and bounded solid D in 3 space. So we have D in space in 3 space. The triple integral of f over D is defined as follows. We have triple integral of the function over D, over the solid D, dV. It is given as limit, as Lmn approaches infinity, a limit of Riemann sum, triple Riemann sum of xi j star, etc., delta V. So the definition of a triple integral is given just as a limit of a triple sum, as a limit of a triple Riemann sum, Okay. A mere generalization of the limit of a Riemann sum for double integral. To just give a meaning of this triple Riemann sum, really we take the solid D. So this is the solid D in a 3 space. We proceed just like what we did with double integrals. We divide the solid into small boxes, and you take one box, arbitrary box. The dimensions are delta x, delta y, and delta z. You take arbitrary point inside the box. We call it x ij star, okay, y ij k star, z ij k star. The volume of this box is delta v, delta x times delta y, delta z. Now evaluate the function f at the arbitrary point here. I get f of x ij star, y ij star, z ij star times delta v. It is like really a hypervolume. It is like a hypervolume, if you want to say. So this is what we do on each box. So this is on one box, you do everything on each box. This will give you a Riemann, a triple Riemann sum, When you take the limit, you get the exact value. This is what we do. This is what we do for the definition of a triple integral of a function of 3 variables on a solid D in a 3 space. Briefly, it is just a generalization of the definition of double integrals for functions of 2 variables as a limit of a double Riemann sum. So this is the definition. Again, just remember that delta V is here delta X, delta Y, delta Z. So that really when you change it to a double integral, it becomes dV. So dV becomes dx, dy, dz in a suitable order. So this is the definition. The next step, of course, how to set up the limits of integration. Just like double integral. How to set up the limits of integration. We'll leave this step for a while here, but before really going to setting up the limits of integration, we have 2 formulas that are really generalizations of the situations in double integrals and also single integrals. So we have 2 formulas. The first formula here, when you find the triple integral of 1, if the function is 1. If the function is 1, we end up with the volume of the solid D. The volume of the solid D. And it is really like, if you recall the double integral of 1 dA over R. It was given as the area of R. For triple integrals, we go in 3 space, which is the volume of the solid. So it is really a generalization of that formula in double integral. Also, the average value of a function for 3 variables on D, f is continuous and D is closed and bounded, is given as the following: 1 over the volume of D times the triple integral of the function d dv. It is also a generalization of the formula for double integrals. If f is a function of 2 variables, the average value will be 1 over the area of R, double integral of f. Here we get h, the volume. 1 over the volume times the triple integral of f. So these formulas are just generalizations really of double integrals and also of single integrals. So this is what we need to know. Now, so the main point now, or the next main step, is really how to set up the limits of integration. Okay. And this will be shown in the second part. Now we come to the main step for triple integrals, which is how to set up the limits of integration. And this depends on the solids, and we have two types of solids. The first one is rectangular boxes, and the other one general solids. So this is what we will consider, but in the process it will be always nice to just recall what we did with the double integrals, because really here it is also some generalization of what we did with the double integrals. So let's start with the first case when D is a rectangular box. So it is described in set notation as the set of all x, y, z in space, points in space, with the x between A and B, y between C and D, z between K and L. So it is just a box in a rectangular in space. We can also write this as just the interval AB cross the interval CD cross the interval KL. So we can write or describe a rectangular box in a 3 space either in set notation or as a Cartesian product of 3 intervals. In this case, the triple integral of any function, continuous of course, over D, over the rectangular box. Here the triple integral, in fact, you can start with the order is not important. Just recall that dv is from the previous part, it is dx, dy and dz. If D is a rectangular box, the order is not important. We can integrate in any order we want. Okay. So here really we have 6 possibilities. Okay. So if we choose, for example, the of x, y, z, and we choose dv to be dx, dy, dz, dx, dy, dz, then of course the dx will go with the inner integral and dy will go with the middle and dz will go with the outer, So the inner dx, the possible values of x are a to b and y c to d and z k to l. So this is H, the first possibility. But of course we can use other orders, other order of integration. So I can choose another way, integral, triple integral of x, y, z. I can choose another one, for example, dz, dx, and dy. So the limits of z will go with the inner, which is k to l, and the middle x will go with the middle integral, which is a to b, and the outer dy will go with the outer, which is c to d. So this is a second possibility. In fact, we have 6 possibilities. If it is dz, and dy, dx, or dx, dz, dy, or dy, dx, dz, or dy, dz, dx. So we have 6 possibilities in this case. Anyone will work, and they all give us the same value of the triple integral. This is the simplest case, which is really similar to the double integral when we integrate over a rectangular region. But the situation is now similar. Now we go to the next type of solids, general solids, and here we have 3 types. The first one, we call it type 1 solids, and it is described in set notation as follows. It is the set of all points x, y, z, such that x, y in R and z between g1 and g2, functions of 2 variables. Graphically, this is the solid. So it is a solid between 2 surfaces, a lower surface g1 and an upper surface g2, a lower and upper. Okay, then we have R. What is R here? R is the projection. Projection of D onto the XY plane. So basically, if we take a point XYZ, a solid, a point in the solid. What is its projection? The projection, you go just the XY, just the X and Y coordinate. So Z becomes 0. So this is what the meaning of the region. So R is just the projection of the solid in the XY plane. In this case, how to set up the limits of integration? Here, we have no choice. We have to start with Z. So here you have the following, double integral of f dv with respect to, you have to start with z of x, y, z, dz. You have to start with z. And what are the limits of z? Well, it is you have the lower surface and the upper surface. So it is the lower limit of integration, the upper surface is the upper limit of integration. So the lower one will be g1 of x1, and the upper one is g2 of x, y. Lower and upper. If it is not clear from the graph how to decide the lower and the upper, usually we take a vertical line. If you take a vertical line, so at a point here, arbitrary point, take a vertical line. Then this vertical line, along the z-axis, you will enter the solid through the surface G1 and you will leave through the surface G2. So where you enter is the lower and where you leave is the upper. And you can say it is really, if you recall what we did in double integration, it is really similar. So this is H. We have to start with the integration with respect to Z. What about the other two? The other two, the double integral here. You integrate over the region R. dA. So after integrating the innermost, you end up with a double integral. A double integral over R, the projection, dA. Well, how to set up the limits of integration here over R, of double integral? Again, use what we did with the double integration techniques, okay, in the previous videos. So once you decide the inner one, the other two, your problem will be reduced to a double integral. We can set up the limits of integration using the previous techniques with double integration. So this is type 1, and this is really a very important type. Once you understand type 1 fully, in fact the other two are really similar. Okay, so always concentrate on in type 1 solids. Try to understand them fully. Okay, now we go to type 2 solids. Type 2 solids are now solids on the ZY plane. We can think of type 1 as solids on the XY plane. Now here these are solids on the YZ plane. So they are described in set notation as the set of XYZ, such that YZ in R and X between H1 and H2. So we have a solid between two surfaces, H1YZ, H2YZ, and then you take the projection of D on R still the projection, and this is HD, this is the solid graphically. In this case, to evaluate, to set up the limits of integration, we have no choice, we have to start with X first. So here, this is H triple integral of X, Y, Z, dx. What are the limits of integration? What are the limits of X? Again, you just go along in the increasing order of the X-axis. If you go in the increasing order of the X-axis, now you enter through H1, and you leave through H2. So H1 is the lower, H2 is the upper. So this is H1, YZ, and this is H2, YZ. Decide the H1 and H2 by moving along the X-axis, parallel to the X-axis in an increasing order, in the positive direction. Then you have the rest is double integral over R, over the projection dA. And we can set up the limits of integration here just using the same techniques of double integration. The third possibility, type 3 solids. These are solids that we can think of them as solids on the XZ plane, But here we have to start integration with respect to Y. So this is off of X, Y, Z, D, dy. And the limits of integration, well, again, go in the positive direction of the Y-axis. Then you enter the solid through K1 and you leave it through K2. So this is K1, X, Y, X, Z, and this is K2, X, Z. This is for Y. Okay. Then the double integral over R dA. Again, R is the projection of the solid on the XZ in the XZ plane. So these are the three types. These are the three types of solids, of general solids in space. Really, if you look at them very carefully, you will see really the situation is really just a generalization of what we did with double integrals. Let's consider the following problem. Evaluate the triple integral of x squared y cosine xyz dv over the solid D, where D is given in this by this definition. Clearly, D is a rectangular box. D is a rectangular box. Is a rectangular box. So to evaluate, of course, we have to set up the limits of integration first. And since D is a rectangular box, really the order of integration is not important. You can choose any order you want. Dx, dy, dz, dz, dy, dx, and you have 6 possibilities. But of course, one should always try to choose the order in such a way that integration becomes simpler. The first, because the function is x squared y cosine x, y, z, it seems it is easier to integrate first with respect to z. So I have only z inside the cosine. So if I integrate it with respect to z, I get the integration becomes a simple U substitution. For example, here, so just if you can see, this is x squared y cosine x, y, z. If I integrate it with respect to z, I have you substitute the derivative here with respect to z is xy, so I have x, and then sine x, y, z. So this is the integral. So U substitution. If you start by integrating with respect to z. So I will start with integrating with respect to z. So this is double integral of x squared y cosine x, y, z, x, y, z, dv over d. This is double integral, triple n. This is x squared y cosine x, y, z, dz, d, dz. So this is the inner, or the first, the inner integral, I will integrate with respect to z. The limits are 0 to 3, 0 to 3. What about the middle and the outer? Again, I can choose either dx dy or dy dx. It is better to wait for a while and see what is the result here. So that then choose the order that will make integration, the next integration easier. Okay. So here, this is S, so I will leave the limits for a while. So this is just integral. Here the integral is just x sine x, y, z from z equal 0 to z equals 3. You can check if I differentiate with respect to z, I get this one. Derivative of sine is cosine times xy, get x squared y. Now this is also double integral. Substitute, this is x sine 3 xy. This is when you substitute z equals 3. Minus when you substitute z equal to 0, you get 0. So this is what we did. Now x sine 3xy. The next integration. I can in fact integrate with respect to x or with respect to y. If I want to integrate with respect to x, I have to use integration by parts. But if I want to integrate with respect to y, then it is a simple U substitution. So it is better to choose to choose U substitution and hence start with integration with respect to y. So I will write here dy, then dx. Then just complete what was left over from the previous step. So this is dy, and this is dx, and this is dy, and this is dx. The middle is dy, so the limits are 0 to 2, and the outer is dx, so the limits of x 0 to 1, 0 to 1, 0 to 2, 0 to 1, 0 to 2. So it is always better to choose the order that will make integration simpler. Okay. The next step is to integrate with respect to y, and here it is just a matter of U substitution. Derivative of 3xy with respect to x is 3x, so I have x, so it is just 1/3, so 0 to 1. When you integrate, you get 1/3 or minus 1/3 cosine 3xy, 3x1 from y equals 0 to y equals 2, and this is dx. So this is the integration, a simple U substitution. Substitute substitute, you get the following: 0 to 1. This is minus 1/3 cosine 6x, this manner here, minus cosine 0, which is 1, d dx. Now a simple integration. So this is minus 1/3 integral of cosine 6x. This is 1/6 sine 6x minus x from x equal to 0 to x equals 1. And this is minus 1/3. At x equals 1, this is 1/6 sine 6 minus 1 minus, when x equal to 0, I get 0, so minus 0, we leave the 0. So this is the answer of this problem. We consider now the following problem. Set up the limits of integration for the triple integral of f over d, where d is the solid in the first octant bounded by the coordinate planes, and the graphs of the two equations. So we need to set up the limits of integration. Of course, d is not a rectangular box, so we have to decide what kind of a solid is d. Is it of type 1, type 2, or type 3? Once we decide the suitable type, the limits of integration becomes very simple. And to decide the type, we have to sketch the solid d. So the solid d is in the first octant bounded by the coordinate planes. So this is x, and this is y, and this is z. It is in the first octant, so the solid is in the first octant, so it is in the octant closest to us, and bounded by the coordinate planes. So it is bounded by the xy plane, xz plane, and the yz plane. It is bounded by the floor and the two walls. And the graphs of z equals 3 plus x squared plus 2y squared, and x squared plus y squared equals 1. So we have to know what is the graph of these two. The first one, this is a paraboloid, so just if we recall, the graph will be something like this. So it is a paraboloid shifted at 3. So this is the graph. So it is the graph of the first equation. It is a paraboloid. The graph of x squared plus y squared plus 1 equals 1 in 3 space. It is a cylinder. Of course, in the xy plane, it is a circle. So this is 1, 1. In 3 space, it will be a cylinder. You shift the circle along the z-axis, so it is a cylinder. This is the graph of the two equations. Now just combine the graphs in one place, and we need the part in the first octant. So here I have so you have here the circle here, the xy plane 1, 1, or the cylinder becomes cylinder. And I have this paraboloid, so this is the paraboloid. So this is the 3. So I have a paraboloid, a solid below the paraboloid. Just to make it clearer here, I just add something like this. So this is a 3 paraboloid, and inside the cylinder, in the first octant. So everything will be here, in the first octant. So I have a paraboloid. The solid is below the paraboloid in the first octant. inside the cylinder, inside the cylinder. Okay. So this is the graph. Now, what kind of a solid is this one? Is it type 1, type 2, or type 3? And it's clearly the solid is bounded below by the coordinate plane, the xy plane, which is z equal to 0, and bounded above by the surface, which is z equals 3 plus x squared plus 2y squared. And the plane here, the xy plane, is equal to 0. So D, the limits of z between 0, it is above the xy plane, z equal to 0, and below the paraboloid, which is 3 plus x squared plus 2y squared. These are the limits of that. So really it is a type 1 solid. The solid is between a lower surface, which is the xy plane, and the upper surface, which is the paraboloid. Okay. What about the region R? Of course, now the region R, it is this part here. The projection of the solid in the xy plane, this is R. And R is just, this is x squared plus y squared equals 1. So R will be the following. The projection in the xy plane, this is x and y, and this is a quarter of a circle, 1 and 1, because the solid is just in the first octant. So we take this part of the circle. Okay. This is R. Now, so this is xy in R. So this is and xy in R. Okay. Now in R, well, is it type 1 or type 2? It is both, in fact. So let's say it is of type 1. So here again, this is y equals root 1 minus x squared. When you solve x squared plus y squared equals 1 for y, this we take the positive 1. So here R will be the following. So this is 0 less than z less than 3 plus x squared plus 2y squared. This is type 1 solid. D type 1, and here as R also type 1 region. Type 1 region. So the limits of y from 0 to root 1 minus x squared. So here if you just take any x here and take a vertical line parallel to the y-axis, then you enter through the x-axis, y equal to 0, and you leave it through the circle, y equals root 1 minus x squared. And x between 0 and 1. So these are the limits of integration. Now for the setup of the limits of integration of x, y, z, dv over d. D is a type 1 solid, so you start with z first. So this is of x, y, x, y, z, dz, then double integral over r dA. The limits of z of 0 to 3 plus x squared plus 2y squared. Okay, so this is for the inner. Now the double integral over r. Again, on r we said it is of type 1, so we have these two. Okay, so just you continue the inner 0 to 3 plus x squared plus 2y squared over x, y, z, dz. Now double integral over r, it is of type 1. So these are the limits. First with respect to y, then with respect to x. and the limits of y are 0 to root 1 minus x squared, 0 to root 1 minus x squared, and the limits of x are 0 to 1, 0 to 1. So this is how to set up the limits of integration. So the main point is really to decide what kind of a solid is this, is the given solid. Is it of type 1, type 2, or type 3? Once we decide that, usually it is not difficult to set up or write the limits of integration. Now we consider the following problem. Use a triple integral to find the volume of the solid enclosed by the paraboloids z equals x squared plus y squared and z equals 8 minus x squared minus y squared. So it is a volume problem, and we need to find we need to use a triple integral. Using a triple integral, we have the formula here. We have the formula volume of the solid D equals triple integral of the function 1 dv over d. So if you want to use a triple integral to evaluate volumes, then we have to use this formula. Then we take D, just sketch the solid D and try to find the limits of integration and then evaluate it. What is the solid D? It is the solid enclosed by the paraboloids. So we just go and make a sketch of this. So this is the solid here. We have the paraboloid z equals x squared plus y squared, and the inverted paraboloid 8 minus x squared minus y squared. So this is the solid D. This is the solid D. Everything between the two graphs. Well, what kind of a solid is this one? This is a type 1 solid, type 1. Because, well, it is just you have a lower surface and an upper surface. If I take a vertical line at a certain point, then I enter through the lower z equals x squared plus y squared, and I leave through the upper, at any vertical line parallel to the z-axis. So this graph is the lower and this graph is the upper. So it is a type 1 solid. So really here, let me say volume of D. Since it is type 1, so then I have to integrate with respect to z. 1 dz. What are the limits? The lower limit comes from the parabola x squared plus y squared, and the upper limit is 8 minus x squared minus y squared. Then I have a double integral over the region R dA. So this is the first step. So it is type 1, lower to upper. I start with integrating with respect to z. Then I have double integral over R. Well, just what is R now? Let's find R. What is R? R is the projection of the solid. When you project the solid in the xy plane, you get the region R. And it is not difficult really just to find. So this is really the intersection. Find the intersection of the two solids to get the projection. So this is R. So if you need to find R, just find the intersection of the two solids. Intersection of the two solids. So equate z, so this is 8 minus x squared minus y squared equals x squared plus y squared. So this is 2x squared plus 2y squared equals 8, and hence this is just x squared plus y squared equals. So the projection R is just the circle, the circular region with radius 2. So this is R, this is x, and this is y, and this is the circle. With center the origin and radius. So this is the region, this is the region of R. The projection of the solid, projection of this solid. So this is R, this is x squared plus y squared equals 4. Okay, so now just integrate. So this is double integral, leave it over the region R, which is the circular region. Here it is z, from z equals x squared plus y squared to z equals 8 minus x squared minus y squared dA, and this is just double integral over R of 8 minus x squared minus y squared minus x squared plus y squared dA, and this is equal double integral over R 8 minus 2 x squared minus 2 y squared dA. So after integrating the innermost integral, we get a double integral over R. Now R is a circular region. Well, in fact, we can use rectangular coordinates, and it is a type 1 or type 2. Or since R is a circular region, it is better in that case to try to use polar coordinates. It will make integration simpler. Since it is a circular region, I will use for the double integral polar coordinates. So I will just convert to polar coordinates. So I have to describe the region, the circular region, in polar coordinates. Well, x squared plus y squared equals 4. This gives us R squared equals 4, and hence R equals 2. And hence, if I take a ray from the origin to the circle, this is R equals 2. Then R, the region R, can be described as R between 0 and 2. The ray goes from R equal to 0 to R equals 2. And theta, I can take this ray from 0 to 2 pi, a full circle. So 0 to 2 pi. So now I write the integral in terms of polar coordinates. So in terms of polar coordinates, I have the following. This is 8 minus 2 R squared. This is the integrand. dA in polar coordinate, it is R dr d theta. The limits of R for the inner is 0 to 2, and the limits of theta for the outer 0 to 2 pi. Next, we just integrate, and these are just simple integrals. So this is 0 to 2 pi, 0 to 2, and this is 8r minus 2r cubed dr d theta. The inner, this is 4r squared minus 2 over 4, which is 1 over 2r power 4, from r equals 0 to r equals 2, and this is 0 to 2 pi d theta. So now just evaluate at 2, it becomes 16 minus 8, which is 8 minus 0, 0. So this is just 8 integral of 8 d theta from 0 to 2 pi, and this is just 8 theta from 0 to 2 pi, and this is 16 pi. So this is the volume of this solid. So first you have to sketch the solid. You know what type of a solid is it? Is it type 1, type 2, or type 3? Then find the projection and then integrate. Well, now we consider the following problem. Set up the limits of integration for the triple integral of a function f over d, where d is the solid bounded by the cone x equals root y square plus z square and the plane x equals 2. So here we just need to set up the limits of integration, because we don't need to evaluate, because f is just a general function. So to set up the limits of integration, we have to sketch the solid d and decide whether it is of type 1, type 2, or type 3. The solid is bounded by the cone x equals root y square plus z square. So it is a cone, or really half a cone, parallel to the x-axis, with the axis whose axis is also the x-axis. So if we go and sketch along the x-axis, we have the half cone. We have this cone. So this is really the cone x equals root y squared plus z squared, and the plane x equals 2. So it is a vertical plane at x equals 2. So it is just a plane on the perpendicular to the x-axis. So you have a cone and you have a plane. Okay. So this is the solid. This is the solid. Everything inside the cone. So now what kind of a solid is this one? Well, the solid is along the x-axis, so it is type 2. It is type 2. So really here, in that case, we have to start integrating with respect to x, because it is a solid along the x-axis, or parallel to the x-axis. We have to start integrating with respect to x. So this is type 2, a type 2 solid. So now the integral, the triple integral of x, y, z over d. I have to integrate first with respect to x. This is integral of x, y, z, dx. Now what are the limits of integration with respect to x? Here, if I just go along the x-axis, I enter the solid through the cone and I leave it through the plane. I enter the solid through the cone and I leave the solid through the plane x equals 2. So the lower will be the cone. So this is root y squared plus z squared. And I leave it through the plane x equals 2, so it is the upper limit. So these are the limits of x. What remains is the double integral over the region R dA. So now I need to find R. What is R? R is the projection of the solid on the YZ plane. So what is the projection on the YZ plane? For that we take the intersection also. We take the intersection, we get something like this. So it is just like a circle. So this is the projection. And to find it precisely, just get the intersection. So here, so this is go to R, again find the intersection of the two solid, of the cone and the plane. So this is root y squared plus z squared equals 2. We equate the x's. X equals 2 and x equals root y squared plus z squared. If we square both sides, we get y squared plus z squared equals 4. So the projection is a circular region in the YZ plane, So I just take the YZ plane here. So this is Y and this is Z, and I have a circle radius. So this is my region, my projection. Okay. And this is Y squared plus Z squared equals. Now, I have to just set up the limits of integration based on this region R. Let's just use here again rectangular coordinates. Of course, we can use polar coordinates, but let's use rectangular coordinates. This region R is a type 1, and type 2, in fact, type 1 and type 2. But I will look at it as a type 1. Now here, at any x here, I enter through, I take a vertical line. This is at any y, sorry. Well, if I take a vertical line parallel to the z-axis, I will enter through the lower part of the circle, and I will look through the upper part of the circle. The lower part of the circle, z equals minus root 4 minus y squared. And the upper part of the circle, z equals root 4 minus y squared. So here for the R, the description of R will be the following. For Z, it is between minus root 4 minus y squared and less than root 4 minus y squared. These are the limits of Z. And the limits of y are from minus 2 to 2, less than. So these are the limits of y and z. Now, so here, as a type 1, the inner will be as it is, root 4y squared plus z squared to 2 of x, y, z. This is dx. Then, for the double integral, it is type 1. So first dz, then dy. So this is dz, and then dy. So this is with respect to z, and this is with respect to y. The limits of z for the middle, they are minus root 4 minus y squared and root 4 minus y squared. And the limits of y are from minus 2 to 2. So this is how to set up the limits of integration for this problem. Let's consider the following problem. Write the triple integral in the order dy, dz, dx. So you have the following triple integral of a function dv over d, where d is the solid in the first octant, bounded by the coordinate planes and the plane x plus y plus z equals 2. So really, here we need just to set up the limits of integration in a specific order. And the order given here is dy, dz, dx. So we have to set up the limits of integration with the first or with the inner to integrate with respect to y, middle to integrate with respect to z, and the outer to integrate with respect to x. So we have to use or to stick to this order. In that case, the first step, as usual, we have to sketch the solid. So it is a solid in the first octant, bounded by the coordinate planes and the plane. So here we have the xyz plane. Well, this is the graph of the plane x plus y plus z equals 2. And to graph a plane, you need 3 points, and the simplest points are the intercepts. So set any two of these 3 variables 0 and find the third. To get 3 points, really, 2, 0, 0, 0, 2, 0, and 0, 0, 2. 3 points will determine the plane. So with these 3 points, join them, we have the part of this plane in the first octant. So this is the part of the plane x plus y plus z. So this is just x plus y plus z equals to the part of this plane in the first octant. So it looks like a triangular plane. The other boundary are the coordinate planes. We have the xy plane, the xz plane, and the yz plane. It is some sort of a solid in the corner of the coordinate plane. So this is the solid. Everything below the plane in the corner. Okay. Now we need to integrate first with respect to y. So here, just let me write the integral here. So this is just triple integral of x, y, z dv over d. And I need this to be triple integral first with respect to y of x, y, z. First with respect to y, dy. So what are the limits of y? Now to integrate with respect to y, okay, so I have to go really through the solid along the y-axis. So you go through the solid along the y-axis. When you go through the solid along the x-axis, the solid is everything is below the plane. When you go through the solid along the y-axis, you enter the solid, we enter the solid through the xz plane. Just remember, the xz plane is one of the boundaries of the solid. So I will enter through the xz plane. So this is n through xz plane. I will enter the solid through the xz plane. What is the equation of the xz plane? It is really y equals 0. And when I leave the solid, I will leave it through the plane x plus y plus z equals. I will leave it through the plane. So what is the equation of the plane? This is y equals 2 minus x minus z. So when I go parallel to the y-axis, I will enter the solid through the xz plane, which is y equal to 0. So the lower will be y equal to 0. And I will leave the solid through the plane with this equation. So this becomes 2 minus x minus z. In terms of types, it is really a type 3 solid if you go along the y-axis. So these are the limits of y. Then over r dA. So first I need to find r. What is the projection of the solid on the xz plane? It is probably obvious that really the projection will be this triangular region on the xz plane. Project on the xz plane, because we are going along the y-axis. The solid is along the y-axis, so the projection will be on the xz plane. The projection will be this region here, this triangular region. So this is really r here. And if it is not clear, again you find the intersection. Usually it helps find the intersection of this plane with the xz plane. So when you find the intersection, the plane 2 minus x minus z, this is y, and the equation of the xz plane is y equal to 0. So this is just x plus z equals 2. So really the equation of this line in the xz plane is x plus z equals 0. So I have the following region. So this is 2, and this is also 2, and this is x, and this is z. And the projection, everything inside this triangle. Okay, so this is the triangular region. This is the projection. This is R. Okay. So this is the region. This is the region R. Now set up the limits of integration for this region. It is given I have to do dz then dx. So first I have to go along the z-axis, So this is x, and this is along the z-axis. And this is x plus z equals 2. So this is really, or equals z equals 2 minus x. Here, this r. So this is really type 1. The limits of z, I enter through x equal to 0, and I leave it through z equals 2 minus x. And the limits of x goes from 0 to 0. It is type 1, and at z, and this is what we need dz dx. Okay, so now this becomes double integral of the inner 0 to 2 minus x minus z. This is of x, y, z, dx. Now dz dx, the limits of z are 0 to 2 minus x, 0 to 2 minus x, and the limits of x are 0 to 0. So this is the writing. This is how we write the triple integral in the order dy dz dx.